Think you know Jupiter? Think again. For decades, scientists argued over what the core of our biggest gas giant was like. Was it solid or missing altogether? Then, in 2017, NASA's Juno mission made that debate irrelevant overnight. The data from Juno suggested both sides were wrong, and revealed a third option no one expected. Jupiter's core isn't solid, but it isn't absent either. It's fuzzy. And that's a problem, because it upends everything we thought we knew about Jupiter's formation, its interior, and even its bizarre magnetic field. I'm Alex McColgan, and you're watching Astrum. Join me today as we uncover exactly what Juno found, explore how a fuzzy core could form in the first place, and reveal why this changes how we think not just about Jupiter, but gas giant planets everywhere. For decades, two competing theories dominated the scientific conversation around Jupiter's core. Many supported the gravitational collapse theory, which suggests that Jupiter formed directly from the collapse of a gas cloud under its own gravity. This would have happened in the colder, outer reaches of the solar system before Jupiter migrated to its current location. In this scenario, the gas giant would have no core at all. It would simply be a layer cake of churning gas all the way through. But this theory didn't have the whole scientific community convinced. Others were almost certain Jupiter's core was solid, made up of heavy elements like carbon, nitrogen, oxygen, magnesium, silicon, and iron. As this solid core grew larger and larger, its gravity started capturing more hydrogen and helium, swirling it together over millions of years to form the planet we all recognize today. Intuitively, this seems to make sense. Our solar system formation models suggest giant planets could be created this way, since ice and rock would condense first in the outer solar nebula, capturing gases in their gravity as they migrated inward. This theory, known as the core accretion model, predicted a dense, well-defined core with a clear boundary separating the compact center from the surrounding layers of gas. To resolve the debate, early missions to Jupiter all took their turn trying to discern what lies beneath the red giant's dramatic atmosphere. By the 1990s, scientists knew that Jupiter was rich in heavy elements, implying the planet was made of more than just hydrogen and helium. The Galileo mission also found evidence that Jupiter's magnetic field must somehow be generated by liquid, metallic hydrogen in its interior. But if the core is purely liquid, how did Jupiter form in the first place? The standard theory of planetary formation requires a solid nucleus to start gas capture. If Jupiter once had such a core, but somehow lost it, how did that happen? Could everything we know about how gas giants form be completely misguided? Despite the successful missions to Jupiter, the planet's structure remained a mystery. The data gathered wasn't precise enough to determine whether its core was solid or diffuse, what it's made of, or how exactly it generates such a massive magnetic field. But that all changed with Juno. On the 5th of August 2011, NASA's Juno mission launched from Cape Canaveral in Florida. Its main objective was to get closer to the truth of Jupiter's composition by measuring its gravitational and magnetic fields with unprecedented precision. Unlike Galileo, Juno was purpose-built to map the planet's gravitational field in great detail, about 100 times better than previous maps. When it entered orbit on the 4th of July 2016, it began tracing a highly elliptical polar orbit, swooping down within just 4,200 kilometers of Jupiter's cloud tops. It did this again and again, from several angles, a path that made this probe incredibly sensitive to tiny changes in Jupiter's gravity. But why are we interested in gravity in the first place? What does that have to do with figuring out what Jupiter's core is made of? Well, we've all seen gravity depicted like this, a perfectly round cone, the same on all sides. I'm sorry to tell you, this diagram is a bit of an oversimplification. For a planet's gravity to be completely uniform like this, the distribution of mass inside it would also have to be perfectly uniform. In reality, if you zoom in really close, their gravitational fields look a little more like this. Planets are made up of many different elements and materials, each with their own masses, densities, and distributions. These differences are reflected as tiny, almost imperceptible variations in a planet's gravitational field. That's why Earth's gravitational field is actually slightly different over mountains than plains, and why scientists are so fixated on mapping Jupiter's gravitational field with incredible precision. As Jupiter's gravity fluctuates, it causes Juno to speed up or slow down. This spacecraft is so precise, it can detect changes in speed as subtle as 0.01 millimeter per second. At the same time, Juno is continuously beaming a steady radio signal back to Earth, which scientists can decode using the Doppler effect. Where gravity is stronger, Juno accelerates, and we perceive a higher frequency wave, while a deceleration due to weaker gravity would result in a lower frequency wave. By repeating this over and over, scientists can build up a very precise map of Jupiter's gravitational field, which directly reflects how its mass is arranged inside. While the Galileo mission managed to paint Jupiter's gravity in very broad strokes, Juno brought it into razor-sharp focus. And what it revealed about Jupiter's core caught researchers by surprise. Turns out, both theories about Jupiter's core were wrong. It seems to have a core, but it isn't solid like we thought. It's fuzzy. Instead of a dense, compact ball, it's dilute, gradually blending with the hydrogen-rich layers above it. It doesn't appear to have any sharp boundaries. It's also much wider than expected, spanning about half the radius of Jupiter itself. The findings quickly sparked a flurry of questions, including whether our understanding of how Jupiter formed needed a refresh in light of this exciting new data from Juno. A popular theory soon emerged to explain this unexpected discovery, that Jupiter once had a solid core to begin with, but a catastrophic collision in its early history shattered and scrambled it in with the surrounding lighter gases to give us the fuzzy core we see today. The only problem is, our standard model for how giant planets like Jupiter form doesn't work without a solid core. So either Jupiter's fuzziness somehow developed later on, or our models are wrong. Anyway, for such a dramatic shattering to occur, the collision must have been massive, possibly with another young planet. Scientists speculate that up to half of Jupiter's core could have originated from the remains of this planet. It was a neat enough theory, except for one unexpected hiccup. A curious team of researchers tried to model this giant collision using a supercomputer. They wanted to emulate the exact event that would lead to the results Juno showed us. So they designed several possible scenarios of a massive object colliding with a Jupiter-sized planet and ran multiple simulations, varying the size of the Jupiter protoplanet and the angle and speed of collision. But try as they might, they couldn't find an event that led to the fuzzy core Juno showed us. Every time they tried, the models did the same thing. The impact would initially rock the planet to its core, but after a while, the dense, rocky material would settle back down again, like sediment at the bottom of a glass. It didn't dissolve into the rest of the planet. A sharp boundary would reappear, clearly separating the core from the outer hydrogen layers. It didn't fit the Juno data, so it was back to the drawing board. Funnily enough, the next clue in this puzzle didn't come from Jupiter at all. It came from its next door neighbor. Well, that is if you consider 648 million kilometers away next door. We've known since 2014 that the waves in Saturn's rings are caused by vibrations inside the planet. This gives us an insight into what the planet's core might look like, similar to how earthquakes let us study Earth's interior. When researchers paired Cassini's gravitational field data with these wave measurements, it painted a staggering picture. These observations show that at least some of Saturn's deep interior doesn't convect. This is a big deal. Inside a giant planet like Saturn, heat is constantly trying to escape. Normally, that happens through convection. It's what is constantly happening in Earth's mantle, or when you heat up a soup. Hot fluids rise to the surface, cool, and then fall back down, only to be heated up and rise again. On and on it goes. If Saturn were fully convective, it would mix heavy elements throughout its interior. There wouldn't be a dense central region at all. The whole thing would be a fully mixed, homogeneous soup. But if it were partly stable against convection, we'd expect to see a gradient of material, with heavier elements concentrated towards the center and tapering outward. And that's exactly what the data shows. Researchers published their findings in 2021, arguing that the only way to explain Saturn's ring wave data, gravitational field data, and partial lack of convection is that it too has a fuzzy core. As it happens, Juno data also suggests large regions of Jupiter may not be convective. We seem to be slowly connecting the dots. If Saturn and Jupiter have fuzzy cores, they likely stem from a common denominator rather than a random collision event. Now, scientists are working on a new, emerging theory of how the gas giants came to be, one in which fuzzy cores are a natural part of planetary formation. We haven't arrived at a neat explanation yet, but it is clear that the old assumptions we had about the largest planets in our solar system are incorrect. Jupiter and Saturn are not made up of solid core and gas envelope, nor do they have a completely mixed interior. Their fuzzy cores are made up of a compositional gradient, with more heavy elements concentrated in the center, which dissolve out into the gas envelope without a clear boundary. This complexity and uneven mixing challenges our current models for planetary evolution. Where our old, simplistic model predicted the giants would cool predictably over time, these new models don't follow the same patterns. And the same is true for all the gas giant exoplanets we've discovered and studied so far. But in the meantime, there is one other jigsaw piece that needs to fit the puzzle created by Jupiter's fuzzy core: its weird and wacky magnetic field. For years, scientists have known that Jupiter's magnetic field is generated through a dynamo process in its metallic hydrogen layer. This layer spans 20 to 60,000 kilometers deep, where temperatures can exceed 30,000 Kelvin and pressures are millions of degrees greater than on Earth's surface. Under these extreme conditions, hydrogen is in a liquid state, but even more incredibly, here, hydrogen's electrons become delocalized or free-flowing. This creates an electrically conductive metallic state. Coupled with Jupiter's fast rotation, this metallic liquid hydrogen creates a dynamo effect, though the exact process of how it's powered remains a mystery. Whatever it's doing, it's working. Jupiter has the largest, strongest magnetic field of any planet in the whole solar system. Its magnetosphere spreads 7 to 21 times the diameter of Jupiter, tapering into a tadpole shape behind it that extends into Saturn's orbit, about 1 billion kilometers away. However, Jupiter's magnetic field also has some quirky characteristics. It's much stronger in the northern hemisphere than the southern hemisphere, has intense, localized magnetic spots, and 2 magnetic south poles. Scientists hoped Jupiter's fuzzy core might actually explain some of these strange behaviors. Frustratingly for them, the opposite turned out to be true. Jupiter's fuzzy core actually complicates rather than explains its magnetic field. Magnetic fields in planets are usually created by swirling motions of electrically conducting material, like the metallic liquid hydrogen in Jupiter's core. However, Juno data show that large regions of Jupiter, like Saturn, seem to be at least partially non-convective. Researchers modeled the fluid dynamics of Jupiter's interior in two potentially non-convective regions to see how they would affect the magnetic field, one in the upper part of the planet's interior and the other lower down, corresponding to the dilute core. They concluded that the upper stable layer helps explain Jupiter's magnetic field even better than previous solid core models. However, the lower region, representing the non-convective dilute core, did not explain Jupiter's magnetic field on its own. In other words, a completely stable fuzzy core produces a magnetic field that's very different from the one we actually observe. Now, researchers believe Jupiter's dynamo is more complicated than originally thought. It's possible that below the uppermost molecular hydrogen layer, Jupiter has a layer of helium, which rains down through the liquid hydrogen, like oil passing through water. Some think this could have an effect on the magnetic field. Another theory claims Jupiter's dynamo doesn't operate in a homogeneous way like it does on Earth, and that instead, the planet's lopsided magnetosphere is the result of variations in density, electroconductivity, or both. But on the whole, no one knows exactly how this magnetic field is produced, or what role the fuzzy core plays in its creation. One thing we do know for certain though, is Jupiter's magnetic field is responsible for the biggest, brightest auroras in the solar system. On Earth, auroras are only visible for a 4 to 6 month window. On Jupiter, they never stop, covering the poles with a dazzling display of colour hundreds of times more powerful and energetic than the auroras we're familiar with. By stringing together far UV images from Hubble's imaging spectrograph, scientists were able to create these videos of the auroras in action. Aren't they spectacular? Despite Juno's discoveries, Jupiter keeps its secrets close to its chest. We still don't know how its fuzzy core actually formed, nor do we know how permanent it is. Is the fuzzy core a stable structure that will endure for billions of years? Or is it slowly dissolving into Jupiter's gaseous layers? What relation does it have to the metallic hydrogen above it? And the resulting magnetic field Juno mapped? Are fuzzy cores just a natural part of gas giant formation? We can't say for certain yet. But one thing's for sure, our current models don't show the full picture. Hopefully with further study, we'll slowly be able to answer these questions one by one. Though, the more we learn, the more questions we'll keep asking. The pursuit of truth is relentless, and it is also perhaps the most human thing we can do. There's something captivating about the colossal, stormy surface of Jupiter. From above, its sheer immensity makes everything seem calm, its colourful bands unmoving and majestic. But if you dove beneath those vibrant clouds, you'd be swallowed up in violent storms the size of planets. If Jupiter is a planet you love as much as I do, then why not capture that beauty for your wall at home? Jupiter is one of the 40 different disk plates we have in our own Astrum collections, which showcase 25 different objects in our solar system and 4 incredible Hubble-inspired nebulae. The Moon collection is based on the moons of Jupiter and Saturn, and the Planet collection comes in 2 different styles, zoomed-in planet horizons or full planet disks with their accompanying moons, all based on real imagery where it was available. I love how they've turned out, so much so that I've put them up in my own house too. These captivating metal posters do a great job of bringing the grandeur and wonder of space to the walls of your own home. And being magnetic, they're easy to install, requiring no drilling or screwing to put up or swap out. Scan the QR code or use my link in the description below and see for yourself. Thanks for watching. I really want to give a huge thank you to our astronauts on Patreon. It's really becoming a thriving community, and I've loved reading all your messages and comments over there. If you'd like to join in, then you can visit the link in the description to become an astronaut and bring the channel more stability than the algorithm.
When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team.
Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.